I defined what multilinear means yet? No? Okay, that's totally fine. I have defined some kinds of multilinearity. What kind of multilinearity have I defined?
Bilinear?
I defined bilinear, that's right. So so this concept is not going to be entirely new. You actually know something that is multilinear, and it might have been defined with that word, and it might not have been. Anyone else know what that other thing is? Say it again?
Is it an inner product?
Inner product is bilinear. A determinant is multilinear, right? So that this term was, I actually used, when I taught 221, I know I said the word multilinear. When you learned determinants, you might not have learned the word, but you did learn the concept. So you are familiar with it from determinants, and you'll see when I make the definition why determinants are multilinear. So let's fix vector spaces. And these are going to be called V1 up through VR and W. And these are going to be over field F. And the field F is just not going to matter at any point through this entire discussion. So F is just going to be fixed. So I'm going to say that a function F, little f, from the product V1 cross up through VR. Remember that the product V1 up through VR, the elements of this are just tuples where you have an element of V1, an element of V2, an element of V3, and so on and so forth. Just to remind you what Cartesian products are. W, this is multilinear if f of, okay, so suppose that you've got some entries here, and then you've got vi minus 1, and then you have a linear combination in the ith slot. So alpha vi plus vi prime, and then you have the next one, vi plus 1, dot, dot, dot. Okay, so what this says is that you have all the entries there's a little v1, there's a little v2, there's a little v3, but in the ith slot, you've replaced, instead of having just little vi, you have alpha times vi, you have a linear combination, right? So this is the standard, the simplest possible linear combination. It's the one where you have we have a coefficient on the first one and then the coefficient of 1 on the second one. This is the one that you use to verify that something is a subspace and all that kind of thing, right? So all the entries are just simply entries of the V's, except for the ith one, which is a linear combination. Then this is supposed to be equal to, okay, alpha f of dot 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 vi minus 1 vi plus 1 dot 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 plus f of dot 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 vi minus 1 vi prime vi plus 1 dot dot dot. So all it's saying is that if one of the entries is a linear combination, then that linear combination, then the coefficients, it pulls out. So it's linear in that single argument. So if you view everything except the ith argument as being fixed, then it's linear in that ith argument. And that's true for all I. So let's say that's true for all I, for all vi and vi prime in the ith vector space, capital Vi, and for all alpha and f, that's all scalars, with, and you should think that the Vj are fixed for j not equal to I. So think of this as being, for instance, the determinant, where all the V's, all the VI's, these are all equal, right? So you're just listing now, let's say, n vectors in one single vector space. So those are going to be the columns of your matrix. And the point is, if you replace a column, well, you did it by rows, I guess. So if you take the rows of your matrix and you replace one of the rows with a linear combination, then the determinant of that matrix with a linear combination in that row is going to be the determinant. It's going to break up as a sum. The determinant where you have if the row is alpha vi plus vi prime, then you're going to take the determinant of the one that's got out. So you're going to take alpha times the determinant of the one that has the row vi plus the determinant of the one that has the vi prime. So this is the notion of multilinear that you've seen before with determinants.
Can I quickly ask, what does a Cartesian product mean when you're talking about vector spaces? I've always thought of them as between intervals.
In terms of what did you say?
I've always thought of them in terms of like intervals of like 0 to 1. Or...
It's not important that they're vector spaces, it's just important that they're sets. So this is just tuples. Where VI is in capital VI.
Okay.
So it's just ordered lists where you have an element in the first one, an element in the second one, an element in the third one, and so on and so forth. So for example, we just did the determinant. So this is going to be VI is F to the N for all I equals 1 up through N. And in that case, we have that V1 up through Vn gets mapped to the determinant of V1 up through Vn, like this. And so we just discussed that one. That's one example. And the other example that we talked about is that if A is in, let's say, F to the n by n, so this is an n by n matrix, then if I take the pair VW and map it, where is, oh, there's W, right. W is the target of this thing. Here I'm just calling them, V and W, and they get mapped to V, A, W, like this, for, this is V is going to be a vector of length m, but it's going to be a row, and W in F and col, this is a column vector, this thing is bilinear. Right? So if you had, so multilinear means multi, but if you had 2 of them, then it's bilinear. If you have 3 of them, it's trilinear. More than that, people don't really say, but you could figure out what language these are coming from. So bi and tri. Is it quad or is it quart? Is the question, right? Is the next one going to be quadrilinear or quartilinear? I don't remember. Have to figure it out. Is it quintilinear or pentalinear? Right? It's a question of whether it's Latin or Greek. Okay, lemma. So if you have V1 cross VR, so that's going to be denoted as the product of the VI, right? So this is the shorter way to write this thing. This is the product, I guess, next to be to write I equals 1 to R of the VI. So if this is multilinear, right? And if you have this thing being linear, mapping to W prime, then, let me take color, just to indicate what I had already written. What can you tell me about the map from the product to W prime? It's also multilinear, right? So that implies that this is multilinear.
Professor, is W prime just some other vector space, or is it the dual space, or some like
it's just some other vector space. It had better, yeah, it had better be another vector space. Otherwise, I don't know what it means for the map from W to W prime to be linear. But I don't mean that it's the dual. So prime here just means another vector space. I'm going to use star for dual from now on.
All right.
Yeah. So the interpretation The interpretation is that if you look at vector spaces with a map, vector spaces W, with a multilinear map, from the product of the V's to W, then this collection of objects just forms a category. And I'm not actually going to define it, but what it is a collection of objects and a collection of morphisms. So an object in this category is going to be a vector space with a multilinear map from the product to W. Right? So here we have an object in the category, a multilinear map. And here we have another object in the category, a multilinear map from the product to W prime. And the point is a morphism is just a linear map from W to W prime. The fact that any linear map may mean is compatible with the multilinearity so if you give me a linear map from W to W prime, then it induces a multilinear map from the product of the V's to W prime. Now, if you gave me a multilinear map, right, from the product of the V's to W prime and the product of the V's to W, then you'd need that the diagram commutes in the sense that when you go from the product to W and then to W prime, it's the same thing as going straight from the product to W prime. Yes?
What does it mean to take a product between these different vectors?
It just means that you're looking at lists. These are just orders. So the product, this thing is just ordered lists of elements. One from V1, one from V2, one from V3, and so on and so forth. So for instance, what is R cross R, or R to the 1 cross R to the 1 cross R to the 1? And if there are R of these, then what is this isomorphic to?
R3. Oh, well, R.
R to the R, right? Right. So I could have made one of these. I could have made this 1, 2 up through R, and then what would this have been? So R plus 1 choose 2, right? The fact that these things are different vector spaces, I can still just list one vector in there, one vector in there, and one vector in there. It's still a perfectly good list. Yeah.
So what's the difference between the Cartesian product notation and the product with I equals 1 to R notation?
What's the difference between this notation and this notation?
Okay, so you're representing the same thing, but
Yeah, they're equal, right? Right. The fact that I chose to write this one out and I chose to write this one with a sum sign is neither here nor there. The same thing here.
okay.
This is just, I chose to write this as a big product instead of writing them individually. It's the same thing. So this is the product analog of the sum vectors. And this is going to come up again, actually, because I could, for instance, have written V1 plus VR and this thing, right? And then today we're going to define another one, which is going to be V1 tensor up through tensor VR. And this is going to be the big tensor product from I equals 1 to R of VI. That's what we're doing today. We're defining tensor products.
Professor,
Yeah.
real quick, just make sure I understood the situation here. So if I have a collection of vector spaces and I have linear transformations between them, then if I have a multilinear transformation from the product space to one of them, I will also have a multilinear transformation to all the other ones.
No,
from the product.
if you have a multilinear transformation from the product to the first one, so what does first one mean? So you have, let's suppose you have a whole bunch of vector spaces, W1, W2, W3, W4, and you have various maps between them, like this, right? So you could say, well, what if I have a map from the product to this one and the map from a product to this one? Then you have to be a little careful, right? you can't just specify that, say, if I have a map from the product to this W2, then it doesn't give me a map to, say, W3. Because there is no, don't have a given map from W2 to W3. It could be
Oh, I get
worse, because it could be that there could be more than one map from W1 to W4. Right? This is what your category of vector spaces could look like. Right? Here's a couple of objects, and there may be 3 morphisms from W1 to W4, or something like that. So if you give me, you know, a map from the product to this W1, then this morphism that goes along the bottom arrow to W4, it gives you a multilinear map to W4. Going from W1 along the middle arrow to W4 gives you another multilinear map to W4, and so on and so forth, right? So the point is that the object in the category is exactly one of these. It is the map, it is W plus the multilinear map from the product to W. Yeah.
So what is a category?
A category is a collection of objects and morphisms. So this is one of the objects. And the point is a morphism is a linear map between the W's such that this map from the product of the V's to W down to W prime is this map over here. So this is a morphism in the category that we've defined over here. Okay, and the axioms for objects and morphisms are not so bad. They're things like every object has the identity morphism. Right, so if I take W prime equal to W and let this thing be the identity map from W to W, then the multilinear map that I have here gives me the same multilinear map that I have there. That's required to be a morphism in the category, that kind of stuff. Associativity of composition and this kind of thing. Okay. So, definition. The tensor product of V1 up through VR is a universal, and this is a word that you have seen before because I told it to you. It's a universal such that. So what I mean is that if you have a multilinear T that goes from V1 cross VR to T. So T is going to be this universal guy. So this is going to be the tensor product, T. So if you have that multilinear map, so no, you don't have, you've been given this one, right? So it's a universal object. So there's going to be a single object in this category, which is going to be T, along with a multilinear map from the product to T. Okay? Such that for all F, all right, so an F is going to be something that looks like this. And let's call that W. All right, so that's going to be, so if whenever you give me a multilinear here, so this is multilinear. So for every multilinear F that you give me, there exists a unique F tilde and the F tilde is going to be this thing, like this, making this commute. So I should say that such that I should be able to finish it. F is equal to, well, let's draw that color. F is blue. F is going to equal F tilde of T. So what that says is that if you have a multilinear map, so there's a fixed thing. Here it is. It's going to map the product to this T. T is going to be a vector space. And there's going to be a multilinear map from the product of the V's to T, such that no matter which other multilinear map you give me, there's always a way to induce it by going through T. And this is then supposed to be linear. Right? So what that says is every multilinear map from the product of the V's to W is induced by a linear map from the tensor product to W. So what you've done is you've made all multilinear maps into just linear maps from the tensor product instead. So you've done you've made multilinear into linear sort of in a universal way, such that now all you have to remember is the linear maps on this side. You don't have to remember the multilinear maps over here. They come from the linear maps from T. So having a linear map from T is the same thing as having a multilinear map from the V's. This is actually much more concrete than it seems at the moment. That's just the right way to make this definition. So, first of all, this shouldn't be completely obvious. T exists. That is, there is a vector space with a multilinear map. It's not just T, but little t mapping the product of the V's, capital T. Right? There is a vector space with a multilinear map from the V's such that it's universal in this category of vector spaces with multilinear maps from the V's. It's called universally repelling because every other one has a map from T into it. So the maps all come out of T. Okay. T exists. Yes?
The object in that definition is the tensor product.
So, okay, the tensor product, so T is a universal such that it's really this. This is really the tensor product, but people will call that guy the tensor product. They'll say that T is the tensor product, even though what they really mean, they say that capital T is the tensor product, when really what they mean is that little t is the tensor product. Right? It's not just the vector space, it's the vector space with the multilinear maps from the multilinear map from the V's. That's really what it is. And you'll see the notation is going to make this fairly clear. So this is the notation. I've already written it, so I shouldn't have to write it again, right? So we write that the tensor product of the V's is the tensor product of the V's, and that's capital T. And so, the map, it takes little, how do I say this? So little v1 tensor tensor vr. What is that? That's equal to little t of v1 comma v0. Yeah. So if you give me vectors v1 through little vr, then their image inside of t is expressed as little v1 tensor up to little vr. Fair enough? Right, because I'm supposed to be taking lists of vectors here, right? Take little v1 up to little vr, and it maps it to little v1 tensor up through tensor little vr. I wrote the same thing here that I wrote over here. So there's not actually anything new. If you can't read that part of the board, it's fine. Right? I'm supposed to be taking ordered lists of elements of the V's to a single element of T. So when I write this list here is a list, this is an element in the product of the V's. And then T of it is going to be a single element of the tensor product. That single element is written by writing little tensor symbols between the V's. Okay, that's just notation.
So I have a question.
Yes.
So the tensor product essentially is some kind of multilinear map?
It is a multilinear map. The tensor product is by definition a multilinear map. It's a map from the product of the V's to T, and that map is required to be multilinear.
I see.
So what we get is, so for instance, I just erased something, and what it essentially says is that V1 tensor up through tensor Vi minus 1, tensor alpha Vi plus Vi prime, tensor Vi plus 1, tensor dot dot dot. Let's write it this way. It says that this is equal to tensor vi minus 1, tensor vi, tensor vi plus 1, tensor dot dot dot. This thing times alpha plus dot dot dot, tensor vi, tensor vi, so tensor vi minus 1, tensor vi prime, tensor vi plus 1, tensor dot dot dot. That's what the multilinearity means, right, Chingwai? Yeah, good. So that's what multilinearity means. Okay, so T exists. So proof. The idea is to construct T by freely multiplying the elements of the VIs, right? So what this is supposed to mean, in some sense, is that you are formally multiplying the elements of of capital V1 up through capital VR. We're just formally multiplying them in the freest possible way with no relations, right? This just says, take an element of V1 and multiply it by an element of V2 and multiply it by an element of V3. If I could do that, multiplication is multilinear, right? If I multiply n things, but I replace the ith one with a linear combination, then that linear combination distributes out. That's the idea here. This is the universal way to multiply elements.
So it's possible that given a certain multilinear transformation, we wouldn't be able to actually multiply them in the way you're describing, right?
What do you mean?
Is that what you're saying? Like what you're saying, you're multiplying them freely without defining such a rule. Is it possible that we could not actually have such a rule between them? Like they would not be multiplied?
You could have a rule. That's an excellent point. Yeah, you could have a rule, but if you did have a rule, then your rule would be a quotient of the free one. It would be you'd multiply them freely, and then you'd mod out by your rule to say that your equations are supposed to be satisfied, whatever your rule was. So there's a universal way to multiply them without any rules, but if you want to impose rules, then you just mod out by some relations. You'll see what happens when I make the construction. It's actually gonna, it sort of explains that point. So what we want is this. I was going to have to write that in the proof anyway. Didn't realize that at the time. But we want this thing, there's just two cases. We sort of want it with, in two cases. One is alpha equals 1, in which case it's just a sum. And the other one is the usual one, right? It's VI prime equals 0. But I want to separate this off. Whenever you check the linearity condition, there's two ways to do it. You can check it for linear combinations of the form alpha VI plus VI prime, or you can do it for let's see now, for just sums and just scalar multiples, right? So we're going to do the sums and scalar multiples separately instead of doing them both at the same time. It'll just make it simpler. Okay. So let's set T equal M mod N. We're going to use quotients now. Or M equals the span of, and it's going to be all lists V1 up through VR, such that VI is an element of capital VI for all I. Okay, so what we're doing is we are taking, way to say this, we are taking a vector space whose basis is the set of elements in this product. Right, so we're saying that, if I take V1, think of these as being column vectors of length n or something like that, right? So I'm not saying that I'm looking at this thing as a vector space and I'm taking a basis for the product. I am not saying take a basis for the product. I'm saying take every element in the product and make each such element a basis vector. So this would be sort of like taking, imagine taking as a vector space, take M to be the span of sort of, you know, x, y in R2, right? So what I have is I have a basis vector E sub 1, 0, and I have a basis vector E sub pi 0, and I have a basis vector E sub, you know, I don't know, pi 2, 0, and I have a basis vector E sub 0, 1, and a basis, so on and so forth, right? Every point in the plane is going to give me a basis vector. That's a lot of basis vectors, right? Now, n is going to be a whole bunch of relations, right? So we're going to modify a very big subspace of this thing. So n is going to be the span of, I hope I have enough room to write this. It's going to be dot, 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 and let's write it as alpha vi dot, dot, dot. And then we're going to subtract off alpha oh, actually, I'm going to do it all at once. I'm going to do it all at once. Let's make this alpha vi plus vi. I'm going to do this. What I'm doing is I'm taking this equation, and I'm just going to write this one minus that one minus that one, and that's supposed to be 0, right? So keep in mind that I've already got inside of M, so M is going to be spanned by lists of symbols, V1 up through VR, such that VI lies in the vector space capital VI, right? So I have these things. Now I'm just going to take any list that has sort of a linear combination in here. I'm going to force it to be equal to alpha times this one plus this one. The way I'm going to force that to be equal is to do this thing, VI prime, and then subtract off alpha times VI, and then subtract off VI prime, like this. Okay, so M is the set of symbols, which you should think of as being these tensor products, V1 up through VR, and I'm going to simply declare, that when I put a linear combination in the ith slot, it's supposed to be equal to alpha times the one with VI there, plus the one with the VI prime there. Right? The n is what you're setting equal to 0, because you're modding out by it. Right? So in the quotient M mod n, here's the point. In M mod n, this guy is equal to this one plus that one. Right? Because you set everything in n equal to 0. So in the quotient, this guy is equal to this one plus that one. Because this one minus that one is equal to 0, because it's in n. Right. Okay, so what do we have to check? So I claim that the product of the VI's, that this injects into M. So this is a map of sets. And it's not linear or multilinear. It's not in any sense linear, but I claim that when you look at the product of the VI mapping into M and then mapping to M mod N, that this thing is multilinear by construction. Remember what I just said, in the quotient M modulo N, this symbol is equal to the sum of this symbol and that symbol. Because this symbol minus that one is 0, it's in N. Therefore, this symbol is equal to the sum of that one plus that one in M modulo N. That forces this map to be multilinear. This is the freest possible way, right? This is the freest possible way you could make a multilinear map, which is to say that let's take all of these symbols and simply declare that multilinearity has to hold. That's what we're doing.
And the injectivity of that map, is that something that we just defined, or did we get it?
Let me be clear. It's injectivity into M. It is not injectivity into M mod N.
Okay, I see.
It's
I thought
injectivity into M, and it's injectivity into M for the silly reason, let me just say, that this thing is a basis for M. Right? M is actually a vector space whose basis is this thing. Right? So this is a basis of M. By definition. Yep.
Why would they not be the same?
Why would they not what?
Be the same.
Be,
The same.
why would not what be the same?
The product of VI and M.
Because this is a basis for that. So elements of M are linear combinations of these elements. So remember, this is like saying, why would 1 through n, why would E1 through En, so what is it, E1 up to En inject into F to the n?
Yeah, but here the VIs are vector spaces.
Doesn't matter. This is a set. This is a set. This is a vector space whose basis is this set. The basis is a subset of this, of M, but elements of M are linear combinations of these things. It's much bigger, right? This is really, so M is equal to F to the product of the V.
So is it correct to say M is linear combinations of sets of bases? Is that what you're saying?
Yeah. Elements of M, by definition, are linear combinations of symbols, and each symbol is an element of this product. So every element of this product is its own symbol, and I get to take linear combinations of these things. Just by definition, it's the span of these things. Yeah.
From M to M mod N being injective, like how many dimensions?
Oh, from here to there?
Yeah.
Hugely not injective. It's surjective by definition because it's a quotient. But think about it. If for instance, if even there's, how do I say this? Even if R is 1, so if there's only one vector space V here, right? Then I'm saying that V, you're taking V and you're making another vector space out of it whose basis is V. So this is going to be an uncountable set. This is a vector space of uncountable dimension. And what's over here is going to have dimension 1 in the end. Because the tensor product of only one thing is just going to be itself. There's going to be nothing to do. What the relations are going to say is that every linear combination of elements of V is equal to the corresponding linear combination of elements of V. Right, so what's going to be left is just every symbol in here is going to equal itself. That's what these relations will say. Yeah, so this N is very big, but N is almost as big. And if all the vector spaces have finite dimension, then M mod N will have finite dimension, as we will see if we get to it today, which we might not. So this will have finite dimension, but M and N each are hugely uncountable in dimension.
Professor?
Yeah.
Could you remind again what does N represent?
Sorry, what does what?
What does N represent?
So N?
Yeah, N.
This one, or M or N?
Yeah, N. Then the
second
N.
one.
Yeah, this
N.
one. Yeah, the second one.
Yeah, so what this is saying is that I have a bunch of symbols.
Yeah.
Right? These symbols are, each symbol is supposed to be a list of elements of the product. A list of elements of the V's, right? So it's an element in the product. And what N says is it's the relations among them. So think generators and relations. So what you're saying here is that, okay, if I have two elements of this product, say, well, three of them, let's say, I've got one of them, right? This guy is a basis vector of capital M. And it's the basis vector that has some V's and then a linear combination in the I slot and then some more V's. And I'm saying that's supposed to equal alpha times this basis vector plus this basis vector.
Oh, okay, that makes sense. Yeah. Thank
Yeah,
you.
it's imposing the relations of multilinearity in some sense by hand. You're taking
that makes
all of the symbols and declaring that this symbol should equal alpha times this one plus that one.
Yeah, thank you. Yeah.
Yeah. Okay. So let's suppose.
Professor,
Yes.
can a multilinear map ever be surjective? Because you can have things like Bell states, which by definition you can't map from an element to.
Okay, you win the prize here. So let's put an aside here. And the question is, does every element of the tensor product have the form little v1 tensor up to little vr?
No, it doesn't.
The answer is no. Just to be clear though, this is the question that Jack just asked. And the answer that Nicole just gave me, I think it was Nicole, I can't tell because there's masks on, I can't say who said it. The answer is no.
Does that imply no multilinear map is surjective?
Well, no, it doesn't imply that no multilinear map is surjective. If R is equal to 1, for instance, then you just get your vector space back.
Oh. Okay.
Right? But pretty much as soon as R is not 1, or as soon as the dimensions of these spaces are bigger than 1, in trivial cases, these things are surjective because all the vector spaces have too small dimension and they have to be surjective. But as soon as the vector spaces are bigger, they're not surjective anymore. Let's give an example. Let's do an example of a tensor product right now before we do the proof. So we're in the middle of the proof here. We will finish the proof in a bit. Let's do an example first because it might help. So this is a crucial example. How about if we take V to be F n, oops, let's take it to be F n rho, and let's let W star, oh, yeah, I'm going to call it W star, even though that will be a little bit confusing at the beginning, but Fm, and that's going to be call. Okay, what this means is that W, it means really that W is F to the M rho, like this. Right, so the dual of the row vectors is the column vectors. Yeah, so then what is, if you give me a V, little v in there, and a little w in there, so that's going to be a row vector and a column vector. What is, I haven't written that diagram, I probably need it for the proof. So what is little v tensor little w in capital V tensor capital W star? Let's call, instead of calling this little w, let's call this phi to make it clear that it's a linear function. Okay? So this is going to be V tensor phi. Don't tell me I got it backwards. By row times a column, I got it backwards. So my notes are backwards on this count. So what is going to be V tensor phi? I claim that V tensor phi is going to be, it's going to be phi times V. So phi is a column vector of size n, right? And then we have a row vector of size n. So that's going to be phi, that's going to be V. And the product of these things is going to be an m by n matrix. And this is going to be V phi. So what we're doing is we are taking the entries of phi and multiplying them by the entries of V in the freest possible way. So I claim that, that V tensor W star
Wait, is that CV or VC?
This, I'm sorry, is V. What did I write down? Yeah, VV. Yeah, that.
So is V tensor W star the set of rank 1 n by n matrices?
Yes, that's going to be the point. Right? So this has rank 1. But there are lots of matrices that have rank bigger than 1. Now, that's only true if if both m and n are bigger than 1, right? If m and n, if one of them is 1, then it isn't true that there are matrices of rank bigger than 1. But it's only true that there are matrices of rank bigger than 1 if there's at least 2 rows and 2 columns. Right. So V tensor W star, what is the set of all matrices here? The set of all matrices, this is going to be Hom from V into W, right? It's going to take it's going to take column vectors. I'm going to have to fix, I'll fix what my notes say later. So Hom from V into W, that's going to be all linear maps from V into W. And the map is that it takes V tensor phi to X. It's going to be a linear map, right? The linear map is going to take X to phi of X times V. And I don't expect you to sort of parse this right now, but look at it later and see what that has to do with the matrices that you've written down over here.
And the phi v's are the bases for that Hom?
They're not the basis exactly, but they do span.
Oh, okay, yes.
A basis is going to be the phi v's, so a basis, and we'll prove this, a basis is going to be V tensor phi, such that the v's lie in a basis of V, and the phi's lie in a basis of W star. So if you take a basis for V and a basis for W star and then multiply those, then you get a basis. What that's saying is if you let these things be standard basis vectors and let those things be standard basis vectors, then the matrices that you get this way are standard basis vectors of the tensor product, which you've seen before, because those are the matrices that have 1, 1 and all the rest zeros. Yeah.
But here
online, go.
Yeah, so but here you kind of assume that V and phi sort of live in, I guess, kind of different spaces, but even V and phi lived in pretty much the same space, which just taking an example from physics, which is the zero linear combination of the 1 and 0 state, and
right.
They add it to 1, then you could still have the matrix, like as in elements in the tensor product that doesn't.
Yes, that's right. That's right.
Would you still form a matrix? Would you still form a matrix that way? Because you can't write just V is sort of perpendicular to phi anymore.
Don't really want to write it as a matrix unless you've written one as a row vector and one as a column vector, and then you take their tensor product is equal to their product. Okay. But you can always, and we'll get to this. This is a really good introduction to what we're doing later. Well, it's supposed to be today's lecture, but we probably won't have time. Which is you're supposed to say that if you have a basis so if you've got a basis for V1 and a basis for V2, so let's let this be B1 and let this be B2, then what you get is that V1, how do I say this? It's going to be V1 cross V2 is a basis for V1 tensor V2. And what that means is that, so what is this? This is going to be V1 comma B2, where this is, maybe let's call it E1. No, E1 V2. So you should think of this thing as being E1 through E1 through EM, and this as being E1 through EN. Right? So you're looking at now products of a basis vector of f to the m and a basis vector of f to the n. And that's going to give you these EIJs. So you can always say Jack, you can always say that your element is going to be a linear combination of these basis vectors.
Right.
Whether you want to write whether you want to write an element of this basis as a matrix is kind of up to you, but you can always write down this basis.
I see. Thank you.
I'm a bit confused as to how this example is a counterexample to the fact that okay. So what are all matrices in the tensor between so I get that these give you rank 1 matrices.
Yes.
But if
No, the image. This is the image of, so this says that if we look at V1 cross V2, V cross W star, we have a map from V cross W star to this vector space. The image is the set of rank 1 matrices.
And that vector space includes more than rank 1 matrices.
Yeah, it includes all m by n matrices. So this is all m by n.
Okay.
Yeah, so this is all m by n matrices as a vector space. This multilinear map, the image is only the rank less than or equal to 1 stuff. Yeah? So you don't get all of the matrices as pure tensor products of a vector and another vector, or a column vector and a row vector. Yes?
Just about like writing, when you wrote V tensor W star equals HOM VW.
HOM, this says HOM.
Okay.
So this is the set of homomorphisms from V to W.
Okay.
Yeah. Is that what you're asking?
Yeah.
Yes, this is the set of homomorphisms from V to W. If you like, in the category of vector spaces, this is the set of morphisms from this object to that object. So you look at the category of vector spaces that has objects being vector spaces and morphisms being linear maps. So if you give me 2 objects, you can look at the set of all morphisms from this one to that one. In this case, so it's written as HOM for homomorphisms. And when this is f to the n and this is f to the m, then this is just going to be f to the m by n.
Okay. And these it just happens to be homomorphisms because V and W are both vector spaces, right?
Yes, so V tensor W star is always going to be HOM from V into W. And here's the map. It tells you exactly what the map is. Let's finish the proof because we can. It doesn't take all that long to finish the proof. Let's see. And the end of the proof is satisfying. So what do we have? Will you allow me to erase this board? Yes? Okay, good, because I want to continue the proof sort of after the previous paragraph of the proof. I had intended to do all this anyway, by the way. This is at the end of the lecture notes. Jack just asked the question before we were done with the proof, which meant that we should do it now instead of later. It's totally fine. Okay, so we have our injection from the set of elements in the product as a basis of M, and we've got N as a set of relations among those basis vectors that impose multilinearity. That is, the map from the product of VI to M mod N, this is multilinear literally by construction. Okay, so what? So let's suppose that we have a map from the product of the VI by a map F here to W. Like this. So we've got this already. Yeah? That's given. That's our map that we have here. That's really this thing, just to remind you that it's this injection. That's given. Suppose that we have this. Suppose that we have our F over here. Okay? Period. Then I claim that we get, what color did I have it? Was it red? What's the downward arrow color?
Green. Red.
Downward arrow is red, right? Then this. What?
I think it was red or orange.
It was red because I didn't use orange. It doesn't show up all that clearly. Then we have the down arrow because the product of VI is a basis of M. Think about that for a second, right? The product of the VI's is a basis of capital N. So this is a vector space whose basis is this set. So I can take, because these are vector spaces, that's a vector space, that's a basis, I can define, remember we proved very early on, I think in lecture 1, that homomorphisms from M to W are the same thing as set maps from a basis to W. So if you give me a set map from here into W, it's the same thing as giving a homomorphism from M to W. Right? Just tell me where the basis vectors go, and that determines the linear map. So that's by lecture 1. That's an exclamation point because it's one of those things you have to step back and go, oh, yeah, that's right, it does. If you want to define a linear map from a vector space to another vector space, just take a basis of the source and just tell me where the basis goes, and that's it. You can send them wherever you like, and wherever you send them, you get a unique linear map that does that. Okay, but F is multilinear implies that N is contained in the kernel of this down arrow. Right? Because if you take an element in here, a list of vectors, right? And if this list of vectors had sort of an alpha plus v, alpha vi plus vi prime there, that mapped to some element of W, and this guy maps to some element of W, and this guy maps to some element of W. If F is multilinear, then the image of this one is equal to alpha times that one plus that one in W. Right? What that means is that this relation holds in W. If F is multilinear, then this relation holds by the time you may take it to W. And that means that N is contained in the kernel of this down arrow. What do we know about universal property of quotients? Here we have a vector space homomorphism. It contains N in the kernel. What do we know about universal property of quotients? It factors through what? So this implies the universal property of quotients implies that down arrow factors through M mod N. What that means is that M down arrow to W induces unique M mod N to W. And that was what we wanted. That's T. So what we just did was we wanted a universal property for one kind of object, and this being Math 403, where you learn about universal properties for the very first time, we only know one other universal property. And you can use that other universal property to produce this universal property. All you really have to do is express T as a quotient in some universal way, then you can use the universal property of quotients to prove the universal property of the tensor product. I find that very satisfying. What you do is you construct the tensor product in the freest possible way. You take its generators and its relations, and then you show that the vector space that you get by taking the quotient of the generators by the relations has the universal property that you want because it's a quotient and quotients have the appropriate universal property. The point is that these relations exactly express the multilinearity of the map from the product of the V's to M mod N to T. That's the point. These relations exactly express the multilinearity in the freest possible way.
Sorry,
yes.
the bottom says M to W induces a unique. What is that statement? M of N.
M modulo
W?
N to W. It induces a unique map from M modulo N to W.
Okay, I see.
Let me rewrite that more neatly. M modulo N W. That's what it means to factor through. It means that the map from M to W is actually, can be factored as M to M, really M to M mod M modulo W.
Okay.
Right. And that's what we wanted in the first place.
Thank you.
Okay, so next time we'll talk about the basis stuff. We'll talk about a basis for the tensor product, and then we will do exterior products as well.